This is an extended periodic table. Here we have S block in white, stable, red, radioactive. Orange is not discovered yet, but they're all radioactive. These are expected in some models, but not guaranteed. I mean, even up to ultimium, right? 173 is not guaranteed. You might stop sometime before then. But we made some calculations and made some models, and that's where a lot of it ends. They end here. Now, would we ever achieve that? Maybe not. But as you can see here, the S block is 2 elements wide. The P block is 4 more elements wide, so 6. The D block is 4 more elements wide than that, so 10. The F block is 4 more elements than that, so 14. And the proposed G block would be 4 more elements than the F block, so 18 at least. Okay, so this would be the 8th period, all the way from 119 to 168. That's a huge period. 50 elements. And then you would have 5 to 7 more in the 9th period. If you want to see a smaller version, let's start over here. So it's the same stuff. Oh my god. Okay. In blue is stable, discovered. Red, radioactive, discovered. Everything past bismuth plus technetium and promethium. We're just including bismuth as part of the stable because it's so close to stable, and because it's usually considered stable, even though it's technically not. We're doing it for the sake of this video. Orange is radioactive, not discovered yet. Same with yellow, but it's also technically part of a different model. That's why it's a different color. This is the same thing, but based on metal element type 2. It's the same thing over here on the left, but then we have metalloids in purple there, 6 of them. Non-metal stable, non-metal radioactive, non-metal radioactive undiscovered. These are unknown because they're incredibly radioactive, so that's why they're unknown. This is also unknown, radioactive and undiscovered. Okay, if you want to simplify just by element type, we have all these in blue here are metals. That's a lot of metals. Now, the extended periodic table makes the metals look even more dominating. Honestly, the metalloids are teensy. There's just 6 of them. The non-metals, I think there's like, let's see, 1, 2, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. What? No. What? 10, 13, 14, 15, 16. Yeah. Interesting. Oh, I think it's because of my other model, or my other one. Oh, before we tell that. So yeah, all the noble gases we would expect to be nonmetals. Tennessine and acetine we don't know about, unknown. Same with I mean, that could probably be the same color as this one, honestly. These could probably all be the same color. Just ignore that. But this one is not discovered yet. But all three of these are unknown properties in terms of element type. And also they have a lot of unknown properties. The easiest one to study might be astatine. It would have the longest half-life because tennessine has a very short half-life. Whatchamacallit over here, 167. What's that one? What's 167 again? Let's see. Kirchhoffine would be wildly radioactive, like very radioactive. Like, I don't think our scientific instruments are fast enough to record its decay. And that's assuming that it's possible. Assuming that it's possible, which it should be, right? Nothing preventing it from being possible. There's just limitations in terms of our technology of actually synthesizing and recording such a crazy unstable element. Yeah, just so many metals. I mean, it's too many. The 8th period would be 48 metals, 1 unknown and 1 non-metal. Most likely this one is a non-metal or metalloid. It's probably unlikely to be a metal. Although, if astatine is a metalloid and tennessine is a metal, then you would expect for Kirchhoffine and boron to both be metals, technically. That's what you would expect. It's not guaranteed, but... And if polonium and astatine are non-metals, you'd expect tennessine to be a metal, at least Kirchhoffine to be a metal, and then maybe boron here would be a non-metal still. I don't know. How would you color it? But this is the way you have to color it, by being honest, is that these three are too radioactive to tell. We do know polonium's a metal, pretty well understood. And since elements get more metallic as you go down the periods, we would expect the ones under it to also be metals. So livermorium and shit, what's this one called again? Livermorium and Hyxium would still be metals, is what you would expect. Obviously every one of them to the left is. But then tennessine, Kirchhoffine, we don't know. We don't know, especially Kirchhoffine, because one, we don't even know it's possible, because that name was given to it by a fandom, basically. We don't know if it's possible. If it is possible, it's so radioactive that it would be very difficult to study, or to even detect its existence is very difficult. To synthesize it is very difficult, because it would be one of the most radioactive elements, obviously. It would be pushing the boundaries. Okay, let's go back to the left here. If we want to extend it even further, just for fun, there's ones that I think are not impossible in green here. After 324. I forgot where it said it was not impossible. Everything past here would be impossible, though. It said, there was some place that said nuclei up to 324 protons or something were improbable, but not impossible. Now, obviously, I don't really believe that. I'm gonna say it's incredibly improbable and unlikely, but if that was somehow the case and it extended like to here or something like that, then then whatever, you know. But I think it would end right about here or here is where I think it ends. Personally, I think it ends here, but I would like it to end here. So there's two more elements. And then, oh my god. Okay, hopefully, let's hope this doesn't cost money. It does. I'm not going to pay. Thank you. But yeah, that's just for fun. All those green ones are. And here's what it would look like in terms of blocks. This would be the P block, which is tall as fuck now. D, F. This is the G block. It looks tiny now. And then this would be the H block, which would be 22 elements, or 22 electron, in terms of 22 electrons in that orbital, in that subshell. Before that subshell is filled and it moves on to the G1. For example, right there, or right here. But end on. That's funny. But yeah, I named them just just for fun. Oh shit, I went even further, I think. Poopium. But yeah, end on. Yeah. What's going on? Yeah, it's just massive. Just in case you wanted to look at this, just for curiosity's sake. Phonium. Yeah, I just named them whatever. Almost Relium. Not Relium. Imaginarium. Fakium. That's funny. Limidium. That's cool. Cool name. Um, Obamium. Yeah, that's hilarious. Um, uh, yeah, it makes cesium look like a small atom. Like, it makes it look really small. This one does. Cesium is way up here. Wait, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Well, it would still be closer to this one than to hydrogen. In terms of the start of that, the alkali metals, it would be closer to this alkali metal than to this one, because this is technically in the classification of an alkali metal. This is technically in the classification of a alkaline earth metal because it's in the S block. Although most people put it on the noble gases, above the noble gases, because of its properties. But in terms of its subshell, it's more similar to these. Same with this. Hydrogen's more similar in this subshell compared to these. In terms of how big the atom is, though, a cesium atom would be closer to a hydrogen atom than to the Kazakhstanium here. Because you can see 291 is very far away from 55, but 55 is only 54 more than 1, so that's because there's all of these in between, all these, and there's a bigger gap every period, as you can see. Let's start up here. It goes down 2 from 1 up here. Then, as you can see, it's level over here. Starts right there, goes down 2, then 2, and 2, and then as you can see, there's 2, and it just gets bigger and bigger as you go down. Alright, thanks for watching.